Mechanical ventilation has an adverse effect on the body in many ways, but the most concerning is diaphragmatic dysfunction and diaphragmatic atrophy, where the diaphragm doesn't get an opportunity to do its normal workload. Now, we assume when we put patients on pressure support ventilation that the diaphragm is working, but a lot of the time all it's doing is just triggering the ventilator. Proportional assist ventilation is one of an array of modern modes of ventilation that have been developed to ensure that the patient works their way off the ventilator. Modern modes of mechanical ventilation. This tutorial looks at the concept of proportional assist ventilation. Specifically, the version that has been implemented on Puritan Bennett ventilators, where it is known as PAV+. In my previous tutorials, I looked at all kinds of different modes of ventilation, and these can be neatly characterized as open modes, where the operator has most of the control over how the patient interacts with the ventilator. These include what you might call standard modes: volume and pressure control that may be assist controlled or SIMV, pressure support, and bilevel. A more modern approach is to close the loop. The ventilator senses patient activity using high quality flow and pressure sensors and then dynamically makes adjustments to flow and driving pressure. This may be achieved from breath to breath in the case of volume guaranteed pressure control or volume support, or within breaths in the case of automatic tube compensation or PAV+. These are all pressure controlled modes. This tutorial specifically looks at proportional assist, or more correctly titled proportional assist with load adjustable gain. Well, that's a mouthful. I'm going to start with a very simple but important equation, the equation of motion. Then I'm going to move on to talk about partial ventilator support and the work of breathing before going full tilt into proportional assist. I will make one point from the outset. If you had never seen a ventilator before and knew nothing, I believe that this is actually the easiest mode of ventilation to pick up and use. I believe that many clinicians and respiratory therapists avoid this mode because of inherent cognitive bias. It is really simple. Please follow me in this tutorial. Let's start with a clinical scenario. You're called to the ICU to see Laurence, who's 59 years old and has Guillain-Barre syndrome. He has bilateral quadriparesis and respiratory failure. He's been getting plasma exchange and he has a tracheostomy, and he is undergoing a very slow and ineffective pressure support wean. Is there an alternative to pressure support? To understand this, we need to go back and have a look at different types of partial ventilatory support. On the top here is flow and on the bottom is pressure. Let's start with volume assist control. As we're discussing volume control, I must insert a peak flow rate, the blue dashed line. The patient triggers a breath, and let's work our way around the picture. Everything in red or yellow is patient effort. So the patient triggers the breath, and they do this as part of their own inspiration. The ventilator then generates a flow of gas that pressurizes the airway. On the flow waveform, the patient's sinusoidal flow pattern is here. The zenith of that curve is the patient's peak flow. The green waveform is ventilator flow, and you can see that the patient's flow demand exists entirely within the ventilator's flow supply, so demand and supply are matched. And in the tutorial on volume assist control, I showed you how patients can become dysynchronous, where the patient's flow demand exceeds the ventilator flow supply. Now let's look at pressure support. Again, this is a spontaneous breath. The patient triggers the breath and the ventilator generates a flow of gas proportionate to the pressure ramp, the combination of the patient's negative inspiratory pressure and the pressure support inspiratory pressure level. Irrespective of the effort that the patient makes, the airway pressure will always land on the same spot, marked here with an X, the sum of the PEEP and the pressure support inspiratory pressure level. It's always the same. There are three major problems with standard modes of assisted ventilation. First of all, to make sure that the patient triggers the ventilator when the diaphragm contracts and the ventilator is not triggered inappropriately. 2, making sure that flow supplied by the ventilator matches the patient's flow demands. And 3, making sure that the ventilator breath ends when the patient's breath ends. To understand any assisted mode of ventilation, you must take into account a simple equation of motion. That is, the driving pressure, which is the patient's muscular effort, plus the positive pressure provided by the ventilator, equals the power required to overcome the resistance forces, the artificial airway and the bronchi, and the elastic forces, the tendency for the lungs to collapse in on themselves. This can be put together simply as the driving pressure equals the flow times the resistance plus the tidal volume divided by the compliance. Implicitly, if you know the resistance and the compliance, you can figure out all the other elements by measuring flow and tidal volume dynamically. In this model, the patient is breathing spontaneously, so the pressure that generates flow is entirely derived from muscles. The patient generates negative pressure within the thorax and gas flows along the pressure gradient. In the process, it must overcome both resistance, particularly from the endotracheal tube, and elastic forces determined by the total respiratory system compliance. We decide that the patient needs pressure support. The lungs in this case are normal, but the endotracheal tube is narrow, so the pressure support is targeted at overcoming resistance forces. Here we have set the pressure support at 7 and PEEP of 5. The tube size is 7.5 and it is believed that that is the correct amount of pressure support to be dissipated along the endotracheal tube. And as a consequence, if that is the case, then the patient should receive CPAP of 5 at the end of the tube. But how can you be sure that the patient is receiving sufficient pressure support, or whether they're getting too much? And this is difficult and it's not easily assessed at the bedside using most ventilators. For the next few minutes, I want you to think of the patient as the person on the bench trying to lift the barbell and the ventilator as the personal trainer who is providing assistance. At rest, the barbell is at the equivalent of functional residual capacity, or the FRC that is being generated by PEEP. Once the breath starts and the patient must initiate the breath, the ventilator provides assistance by helping the patient lift the barbell. This is manifest as positive pressure on the ventilator. And then elastic recoil brings it back to baseline and the whole cycle starts again. As clinicians, we try to evaluate or determine how much support the ventilator gives the patient, usually using pressure support, how much lifting the patient has to do and how much lifting the ventilator has to do. This is very, very difficult to actually figure out because once the breath starts on pressure support, the same amount of pressure is delivered. So in this system, I'm going to show you different modes of ventilation and how they support the patient. And we're going to start off with airway resistance. So let's just make the barbell the airway resistant, and the elastance is equivalent to the weight on the end of the barbell. Now, elastance is the tendency of lungs to collapse back on themselves. It's the inverse of compliance or the stretchability of the lungs, but we're going to call it elastance now. The patient's work pushes up the barbell and the ventilator work lifts it up beyond what the patient does. I'm going to introduce here the work of breathing Barre. Now this is only used in one mode of ventilation on the Puritan Bennett machines, but I think it's really useful as an illustrative tool as it will help you understand proportional assist ventilation. The bar looks like this and it measures work of breathing using joules per litre. It goes from 0 joules per litre to 2 joules per litre. There are 4 zones, the most important of which is the green zone that goes between 0.3 and 0.7 joules per litre. This is the optimal location of a patient's workload. Below this is the 0 to 0.3 and above that is the 0.7 to 1 joule per litre, and these are both in yellow. They represent too little work or too much work respectively. The outer zone is usually only occupied by the work of breathing that is carried by the ventilator, so it's very high workload. There are 2 measurement boxes in the work of breathing, one for the patient and 1 for the total work of breathing that includes the patient's work and the ventilator work. The patient's work of breathing contains a red box for elastic work and a blue box for resistive work. That's overcoming the tube and the airways. The work of breathing may change from breath to breath. Importantly, in proportional assist, the patient's work and the total work move synchronously. Now, that would not be the case for other modes, as we shall see in the next few pictures. So you can see this work of breathing bar going back and forth. Let's start with unsupported CPAP. You can see on the left-hand side of the screen that we have a tidal volume measurement and a goal tidal volume that will be recorded. The tidal volume will appear in light blue. The purpose of CPAP is to restore lung volume to functional residual capacity. From that point in CPAP, nearly all the work of breathing to overcome elastance and resistance is provided by the patient. If we use our work of breathing scale, this is what we would see in the situation where the patient is comfortably drawing their target tidal volume. If elastance increases, the patient's workload increases and the tidal volume falls. On the work of breathing scale, everything moves to the right. Now let's put the patient on volume assist control. In this mode, the patient triggers the ventilator and the ventilator does all of the subsequent resistive and elastic work. The major advantage of this process is that the patient can trigger the ventilator, and regardless of compliance and resistance, the ventilator will do the heavy lifting. Hence, if elastance increases, tidal volume is maintained. On the work of breathing scale, the patient does very little work and the ventilator carries most of the burden. If elastance increases, the patient's work of breathing may actually fall. All they need to do is trigger the ventilator and the ventilator work increases. Let's put this on a graph. On this graph, we're looking at volume control, volume guaranteed pressure control, that's PRVC or volume support. And we have two axes, a y-axis that has the ventilator's workload on it and an x-axis where the patient's workload is. Now, if you move to the right on the patient's workload axis, we're looking at increased work of breathing for the patient, which means that the compliance has reduced or the resistance has increased. Moving to the left, the compliance is going up and the resistance is going down, so the workload for the patient is reduced. So you can map the ventilator's workload versus the patient's workload, and it looks like this in volume control. In other words, the more work the ventilator does, the less work the patient does. In pressure support and pressure controlled modes, the patient triggers the ventilator and continued inspiratory effort may contribute to an increase in the flow rate that will overcome some resistive work, but the main impact on work of breathing is delivered by the ventilator, and that always pressurizes the airway to the same level with each breath. We tend to target tidal volume with our inspiratory pressure. Hidden within this is the patient's own effort. This is a graphical representation of pressure support. Everything in red is the patient's own efforts. Flow is in orange and the airway pressure is in green, as I've previously shown you in this tutorial. The tiny triangle before the beginning of each breath is the trigger. As you can see, from breath to breath, there is a huge variability in patient effort. That's in red, those sinusoidal patterns, despite the airway pressure being unchanged. The patient may be really gasping, for example, in the second breath, but this only manifests as a slight increase in tidal volume, and bedside practitioners may miss the dramatic increase in flow demands. If there is an increase in elastance in pressure support or pressure control, then the ventilator work is fixed and the tidal volume falls irrespective of patient effort. Let's put this on the work of breathing bar. In the starting position on pressure support or pressure control, the patient is very comfortable and they're working a little bit anyway as part of the total work of breathing. But if elastance increases, then because the level of support has been locked in, any increase in the work of breathing is incurred by the patient. And then they become distressed, manifesting rapid shallow breathing. And of course, the opposite is also true. If elastance falls, then there is improved lung compliance, for example, after a brisk diuresis. Then most of the work of generating tidal ventilation is incurred by the ventilator, and the patient needs to make very little effort. Going back to our graph, you'll recall ventilator work on the y-axis, patient work on the x-axis. Moving to the left is reduced work of breathing, moving to the right is increased work of breathing. Let's see what happens in pressure control and pressure support. You can see that there is a linear relationship. As the patient's work goes up and the patient's work goes down, the ventilator's work is unchanged. Let's draw another graph. In this case, we're going to put flow and tidal volume on the y-axis, and on the x-axis, we still have the patient's workload. In normal circumstances, the patient starts breathing and there is a direct correlation between flow and tidal volume. The amount of gas that goes into the lungs, small breaths versus deep breaths. With volume control ventilation, if the breath is triggered by the patient's effort is restricted to just that trigger and the flow and volume are constant. Now let's look at pressure support. You can see that once the ventilator is triggered, there is instantaneous flow along the pressure gradient. This combines patient effort and ventilator effort, but that relationship is not proportionate. Indeed, there is only one point where patient load and ventilator load match. Now let's just focus in on pressure support. You can see that compared with the normal line, initially with pressure support, there is over-assistance that diminishes as one arrives at the sweet spot. Beyond that point, there is under-assistance, an elevated work of breathing that leads to gasping and fatigue. So the limitations of pressure assist, that's the assistance you get in pressure control and pressure support, is that while flow is proportional to patient effort, tidal volume is related to negative inspiratory pressure generated by the patient's muscles and ventilator pressure, that is the inspiratory pressure or the pressure support. And that inspiratory pressure or pressure support is fixed. So a distressed patient may gasp, generating massive negative inspiratory pressures that may only be measured by esophageal pressure measurement. And despite this, the frequency divided by the tidal volume and the rapid shallow breathing index may look reassuring. And that is the reason why there is quite a lot of enthusiasm for proportional assist pressure support ventilation or PAV Plus, because it should solve many of the problems associated with pressure support. The original paper on proportional assist ventilation by Dr. Younes was published more than 30 years ago in 1992. Generally, this is abbreviated to PAV these days by most people. And I really do think if you're interested in this, it's worth digging out this paper and reading it. It's really terrific. What you need to know about PAV is that it's a spontaneous breathing mode of ventilation. There is no backup and it is patient triggered. It can be flow triggered or pressure triggered, and it's flow cycled, so it is pressure support. But the airway pressure is controlled by an algorithm in the ventilator that matches patients' work of breathing to ventilator activity. Hence, PAV is an inspiratory amplifier. The ventilator amplifies the patient's breath, and it's a bit like power steering for breathing. The degree of amplification is determined by the proportion of the work of breathing that you assign. It's load adjustable gain, and it works like the volume dial in a music system. You dial upwards to increase the gain, to increase the volume, and you dial downwards to reduce the gain or reduce the volume. Now this can go from 1 to 100 on the proportion of support, but generally we work between 20% and 80%. And when we say 80%, that means that it's 80% of the work that is being done by the ventilator or 20% of work that's being done by the ventilator. The proportion that we set is the ventilator's work, not the patient's work. Just to explore what this means, in this case I have set the ventilator to do 50% of the work and the patient to do 50% of the work. And you can see the airway pressure is monitored by the machine, but it also calculates out the predicted alveolar pressure, so you see two pressure waveforms. Imperatively, this means that in PAV, any increase or decrease in the patient's effort is matched by a proportional change in ventilator support. This means that it should be a supremely comfortable mode of ventilation for the spontaneous breathing patient. And this is the basic operation of proportional assist. In this example, as you can see on the top of the screen, the assist is set to 70%. The patient will do 30% of the work and the ventilator 70%. Let's see what happens. You will immediately notice that the tidal volume has overshot the goal. And if we look at the work of breathing bar that is designed specifically for PAV, you will notice that the patient is in the lower yellow zone for their work of breathing. In other words, not doing enough work. This is easy to adjust. If the patient isn't doing enough work, we need to increase the work by reducing the assist. Now we've reduced the assist to 50%. The patient will do 50% of the work and the ventilator does 50% of the work. Now you can see that the tidal volume has reached its goal and the patient's work of breathing is in the green zone in the work of breathing bar. And that means that we're in a good place. But we want to see if the patient can work just that little bit harder. So let's reduce the assist to 40%. The patient will do 60% of the work and the ventilator will do 40%. And this is achieved by just turning the knob. Let's see what happens. Well, now you can see that the tidal volume has fallen below the goal and the work of breathing strip has changed. You can see that the work of breathing for the patient has slipped out of the green zone into the yellow zone on the upper end, and that means that the patient is beginning to struggle. Notice also that the elastic work has increased. What are we going to do? Well, we need to turn up the support again back to 45 or 50% to get the patient back into the green zone. We're going to increase the ventilator workload. And that is really all you need to know about proportional assist. Keep the patient in the green zone and they're comfortable. Now remember this particular graph. Ventilator work on the y-axis, patient work on the x-axis. What happens in proportional assist is this. As the patient's workload increases, the ventilator's workload increases proportionately. The harder the patient works, the harder the ventilator works. The harder the ventilator works, the harder the patient. Now I just want to explain to you the concept of the sweet spot that I briefly mentioned a couple of minutes ago. This is where the patient and the ventilator's workloads are finely balanced. You'll recall that in pressure support there was a single sweet spot, but in PAV there is a direct correlation between the patient's workload and the flow and tidal volume. The patient with appropriate adjustments can continuously be kept in the sweet spot. When there is deteriorating compliance or increased resistance, the patient's workload can be kept constant as a higher burden of effort is taken by the ventilator and the patient remains in the sweet spot. Hence this wonderful work of breathing bar. The green zone from 0.3 to 0.7 joules per litre is the sweet spot. In PAV, the patient's work of breathing and the ventilator work of breathing are effectively locked together so that the two pointers move in synchrony. In this graph, I have placed the tidal volume on the y-axis and patient work on the x-axis. If we look at pressure support ventilation, you can see that increasing patient effort will increase tidal volume, but this is a relatively flat curve. The ventilator work is fixed. In PAV, as the patient's work increases, so too does the ventilators. So the tidal volume increases linear with increased work due to breath amplification. How does PAV Plus work? For PAV Plus to work, the ventilator must continuously monitor patients' lung and chest wall mechanics. That's the compliance and the resistance in terms of inspiratory volume per unit pressure and inspiratory flow. This is achieved by performing a 300 millisecond inspiratory hold randomly every 9 to 12 breaths. It's not done at a specific time interval so the patient doesn't get used to it. Auto PEEP is also measured by intermittent expiratory holds. Remember, PAV Plus is a spontaneous breathing mode of ventilation. If the patient isn't breathing, you can't use it. The ventilator absolutely must know whether the airway is a tracheostomy or an endotracheal tube, and it needs to know the internal diameter so it can calculate flow resistance through the tube. From this equation, the ventilator can calculate how much pressure support to deliver to the patient to harmoniously amplify the spontaneous breath. The ventilator can only amplify the flow generated by the thoracic pump. The patient must initiate the breath. This illustration shows you the inspiratory pauses that are used to calculate lung mechanics. And if you look at the lower waveforms, you can see the direct correlation between esophageal pressure and airway pressure. The level of support mirrors the magnitude of inspiratory effort. Now that I've explained to you why Laurence might benefit from proportional assist ventilation, remember he has Guillain-Barre syndrome and he's not weaning from the ventilator, I need to show you how to set it up on the Puritan Bennett ventilator. Generally, we'll be going from pressure support or assist control to PAV Plus. The patient must be breathing spontaneously. So we're going to set invasive, spontaneous, and PAV Plus. Now the main settings. The first thing we're going to set is the FiO2 and the PEEP level. There is no reason why these should change from the previous mode. Then moving to the right of the screen, you're going to set your peak pressure and tidal volume alarms as usual. And this is imperative. You must inform the ventilator what airway you are delivering the breath through and the size of that airway. In this case, a size 7 tracheostomy. If you do this incorrectly, all of the calculations that the ventilator makes will be wrong. The next step is to set the trigger, and in this case, flow by of 3 liters above base flow and the expiratory sensitivity are set. The expiratory sensitivity is different from pressure support that uses a percentage of peak flow in its current iteration. This expiratory cycle off in PAV is actually an older approach that cycles off from a flow drop between 1 and 10 liters. The mid zone here is 5. That's where I usually set this, but many clinicians use 10 liters for everyone. Finally, the most important adjustment is to set the percentage assist, and this refers to the work of breathing that the ventilator does, in this case 70%. Any adjustments that you need to make at this stage are made by turning the knob that's located on the front of the ventilator here to the right or to the left. Once we're happy with our settings, we are going to accept all and engage the mode. The mode has been engaged, and now you need to be patient for a minute or two while the ventilator makes its calculations by doing inspiratory holds, expiratory holds, measuring flow, etc. The patient is breathing away, it's perfectly safe. Think about how long it takes for an oscillometer to measure blood pressure. And after a certain period of time, the work of breathing indicators appear. And this is where you look. Give it a couple of minutes to settle. Now you can see that the patient's work of breathing is in the lower yellow zone, indicating that they are not doing sufficient work to prevent diaphragmatic atrophy. So we need to reduce support. And what we are going to do is turn the knob on the ventilator in the direction of patient work of breathing. We're going to turn it anti-clockwise. We're going to reduce the support from 70% to 60%. And now we'll see what happens. The patient now is in the green zone. So this is perfect. We leave them there and see how they get on for the time being. In this situation, we can see that the patient's work of breathing is in the upper yellow zone. They're working too hard and they're going to get exhausted. So we need to increase the ventilator's component of work of breathing. We need to increase the support in this situation from 60% to 70%. So we're going to turn the knob clockwise to 70% and increase the support. And you can see that the patient's work of breathing has now gone back into that sweet spot, into the green zone. Let's zoom out and look at the rest of the ventilator screen. Note that there are 4 different waveforms on the screen. The first we've already looked at. That's the work of breathing power bar. Let's visit waveforms 2 and 3. These are the 2 pressure waveforms. The first is the pressure supported waveform. As always on the Puritan Bennett ventilator, spontaneous breathing is represented by an orangey red line. This waveform will be variable in appearance due to the combination of patient flow demand differentials and some end inspiratory and end expiratory holes to calculate mechanics. The other pressure waveform is the grey shaded area, and that is the ventilator's prediction of what the alveolar pressure looks like. As there are no manipulations that you can make to change these waveforms, they're really only decorative. The 4th waveform is the tidal volume waveform, and it gives you an idea of the breath-to-breath variability of tidal volumes. Again, orange means spontaneous effort by the patient. PAV Plus works well because it semi-continuously performs lung mechanics measuring compliance and resistance. You can see that this patient's compliance is very good, but the resistance is modestly raised. That translates to the work of breathing for the patient being dominated by resistance work rather than elastance work. The other critical measurement that the ventilator does is to determine the auto PEEP level. In this case, it's a negligible 1.1. Often you would expect to see a high airway resistance and high auto PEEP simultaneously, but don't take that for granted. I will deal with the potential problem of auto PEEP in the next tutorial. Let's put Laurence on PAV Plus. As you can see, he starts off on pressure support. We've got to change that in the change screen, and look at all the settings. He's on a tracheostomy with a 7.0 tube, a few little changes, but most things are fine. And we'll engage PAV Plus. And initially you'll see the pressure support level is quite low and the tidal volume is quite low, but it gradually builds up as the computer inside the ventilator makes its calculations. Now we've numbers on the top and the work of breathing bar is engaged, and we need to give this a minute or 2. You can see tidal volumes are generous and the patient is well inside the green zone or the sweet spot, so we're going to reduce the support. We're going to go down to 50% and see what happens. Let's give him a few seconds on 50% and watch the work of breathing bar. You see it's gone over towards the upper yellow zone. So this is not enough support for him and his tidal volumes are beginning to fall. So we're going to have to push up the support a little bit. Let's go to 55% and see what happens. And on 55%, I think this is a much better place for him. He's still inside the green zone, good tidal volumes, and looks very comfortable. So let's look at the basic operation of how we manage a patient on PAV Plus. First of all, is the patient breathing spontaneously? They can't go on the smooth if they're not breathing, so yes, they're breathing, and we're going to start on 70% assist. I think this is a good place to start. It's relatively conservative, but the patient won't run into any trouble. If after a period of time the respiratory rate is less than 35 and the tidal volume is satisfactory, what we're going to do is reduce the assist by 10 to 20% every 2 hours and follow the patient along. If they remain non-distressed, we're going to wean down to 20%. If they're on 20% for an hour or so and there is no distress and the patient is awake and they're obeying commands, they're protecting their airway, and you're not suctioning them 3 or 4 times an hour, then go ahead and extubate the patient or put them on high flow. If they do become distressed during this period, look at the various components of their breathing pattern. If the compliance is falling, you can increase the PEEP. That should help the patient onto a higher part of the volume pressure curve and maybe reduce the workload of breathing. If, on the other hand, the problem is rapid shallow breathing, the respiratory rate is greater than 35, then you've got to increase the assist. Have a look at this example. What do you think? The patient's work of breathing is quite low. You may balk at increasing the support because of the modest tidal volume, but bear in mind that this patient only weighs 50 kilograms. So it's actually okay to reduce the level of support down to 70, 60, or 50%. Different patient here. Have a look at the screen. What do you think? The work of breathing is sitting on the border of the upper yellow zone, and the tidal volume is modest for a 58 kilogram patient. I would suggest that more support is needed and that we would go up to, for example, 55 or 60% and reassess. This is the same patient at a later stage. What do you think? The work of breathing is safely in the green zone and the tidal volume is generous, but the level of support is really modest. This patient's only getting 20% support. So if the patient is awake, protecting their airway and able to clear their secretions, they can be extubated. Let's review this tutorial. In this tutorial, I introduced proportional assist ventilation and I explained the coupling of patient effort and ventilator support. I explained why pressure support is limited and how PAV Plus, that's the Puritan Bennett copyrighted version of this, supports the patient workload linearly. It's like power steering on the ventilator. I then explained how to set up and operate PAV Plus. Next time, I will discuss PAV Plus and auto PEEP, known problems with PAV Plus, and frequently asked questions. I'll see you then, and I guarantee you'll learn something. So that was proportional assist ventilation. I hope you found that useful. If you did, please hit like now and subscribe to my channel and follow me at ccmtutorials.org.